these are just, I will just briefly run through just a few key facts of it. I mean, one thing is that the solar photovoltaics is not heat activated, it is light activated. So, I think we all know that sometimes we tend to feel that, oh, it is very hot, therefore, the photovoltaics should generate a lot. But I mean, it's so please make that distinction between a hot environment and a brightly lit environment. Okay. So, and a few things, just being light, any light does not excite photoelectricity in all materials. So, you have to have actually a specific band which excites a particular kind of photoelectric material or photovoltaic material. So, and we are looking at a pretty small range, and that is sunshine, and even within a smaller range of that is what excites the photoelectrons. So, we are still looking at a very small range of the spectrum, but still we have enough sunshine even in that range to power up a lot of I mean our appliances or activities in this whole world. So, now just a brief history. I mean, this year is quite interesting, because this is exactly we are exactly 100 years from the first experiment which proved, I mean, the 100 years from when experimental proof was obtained on photoelectricity. Of course, it was proposed, and the whole entire theory was put forward in a couple of years, around 10 years before. But this is so today, this year is pretty interesting. We have just crossed this is the centenary year of experimental, I mean, real world feel of photoelectricity. Now, I mean, I am not going into a lot of the details. It's what is interesting is there has been a very continued activity in that area, and although it was not always so well publicized or well known in the public domain. A few interesting things was, we actually started from 9% efficient PV cells, which was about 1958, and when 14% cells came up, and everyone started getting excited about it. And if you look at the 1970s, there was a reduction in PV photovoltaic cell price from $100 per watt, which was an exorbitant amount, to $20 per watt. By the way, just to give you a comparison, today's price is about 57 cents per watt. Okay, so that's, and this is like 1970s price, and this is 2015 price. So, put in inflation, and you can imagine how much we have kind of, what's the huge stretch that we have covered so far. And okay, even we might be wondering about megawatt scale PV plants, but then I mean this has a very long history. I mean, it goes back really far. And if you look at these numbers like 9%, 14%, and today just this year, I mean University of New South Wales, they said that they have come up with a 34.5% efficient solar cell, not the module, just the cell. Okay. So, I mean these are just snippets. There are plenty of things which have not been mentioned and which have happened. I mean, very interesting stuff. One thing was, nobody gave up hope in even at any of these stages. See, $100 per watt even on those days was, I mean, frightfully expensive. Even $20 per watt was frightfully expensive, but then nobody gave up hope. So, that was what is interesting. And today, of course, we are reaping all that benefit. Just to bring into just to keep it at the back of the head, the conversion efficiency really does not amount to any monetary loss directly. I mean, it's not something that you have paid for and you're not getting back. I mean, in a way. So, people can live with a less than quite a lot less than 100% efficiency. I mean, forget it, 100% efficiency is a story. I mean, the theoretical limit is much lower. It's around 35-40% or something. Now that's where we are. Now there are some a few things about orientation and stuff. I mean, normally we tend to wonder why, what is the whole mystery about this tilt of solar panels. Supposing solar panels are deployed in a particular geographical location. So, sometimes we wonder about what this whole business of the tilt is. So, it is just to make sure that one actually faces the sun directly. Now, if you treat the sun as an extended source, which probably one can under certain circumstances, and so if it has to face the normal sun's rays directly normally, then it has the angle of tilt with respect to the horizontal has to be pretty close to the latitude angle. I mean, these are under assumptions like the earth is a perfect sphere and all that kind of stuff. But okay, our real life experience is you get a number very close to the existing latitude wherever you are in. In Kanpur it is about 26.5. So, our experience is that it is around 23, 22, 23 roughly gives us the maximum energy harvest. So, that is just I mean, in passing, and these are some of the terms that we tend to get bombarded by anybody talking about solar. So, this is the direct normal irradiation. So, now supposing this is exactly what I was showing in the earlier slide, that if the solar panel is directly normal to the sun's rays, then the total radiation that it gets, I mean, or averaged, of course, this is averaged over a year and all that. So, that is the direct normal radiation, and this is the global horizontal irradiation. That means, if I have a panel which is exactly horizontal, placed on horizontally on the ground, what is the total energy that is falling on it. So, that has a component of the direct radiation and part of diffuse radiation. There will be reflections from the clouds and other objects in the vicinity. So, all that adds up, and this is the total radiation that a panel, but lying horizontally, just parallel to the ground. So, these are some of the terms. Okay. So, now just get into the, I mean, I am an electrical engineer and I am not in the area of semiconductors design. So, really I do not work in the area of I mean, design of the photovoltaic materials. But what I rather like to see is, I am more of a circuits guy, and I would like to see, okay, let us take a cell, assume that okay fine, it is doing its best, but then how to ensure every source is kind of has some its own idiosyncrasies. So, how to extract the best that I can under the given circumstance. The given circumstance are I mean, the parameters are specified by the available sunshine, the direct radiation, the temperature. Okay. These are the two most important features. Of course, sunshine in when I said the available sunshine, I also take into account the shadows. I mean, shadows which could be transient, for example, a cloud passing by, or a whole flock of birds passing over, or maybe slightly a little slower. I mean, the passage of the shadow might be a little slower, because while the sun is moving throughout the day, it may be getting obstructed by certain buildings, trees and other such structures. So, these are kind of things that what I mean by available circumstances. Now, in those available circumstances, the cell has the solar or the whole panel is capable of giving a certain maximum amount of sunshine, electrical energy. Okay. But that electrical energy does not come out naturally. It is not something, okay, under this circumstance, here is a tap. If you open, you will just get that amount of energy. You have to make sure you open the tap exactly properly. I mean, we all know, like what happens, I mean, the story of the tank and the range and all that stuff. So, this is what as circuit guys, this is how I would like to look at this is how the cell would be modeled. Okay. So, you have a diode which kind of represents the recombination inside the material, and this is a loss which is associated with the in the shunt, and if I am drawing this current out into the external world, then also there is a loss associated with it. I mean, there are plenty of factors in each of these. I am not really getting into that, and IPV is the actual photo current. I mean, the current bunch of electrons released by the sunshine. So, now this is where we actually start our work from. Now, this is the IV characteristic and this is a PV characteristic. I mean, there we see these curves like left, right, center these days. Okay. So, there is nothing new in that. All that I want to point out is that we will start from the power curve. Actually, the power curve is just derived from the IV characteristic. This is the primary characteristic of the solar cell. Once we get that, we take for every point along this curve, we take the voltage multiply it by the corresponding current and get a value for power. So, I replot it as power versus voltage. It is just directly derived from the left hand curve, and we get such kind of stuff. Now, it's obvious. I mean, when it's in short circuit, the power is 0, and when it's on open circuit, obviously the power is also 0, because either V is 0 or I is 0. So, so these are the two ends of that curve, and just this there is this guy Demovas who said something similar about when a function has at two different values of the argument has the same value, probably it has it's flat in between or has a critical point somewhere in between. Okay. So, now fortunately they do not turn the other way. So, they all have a maximum, and all that we want to do is to access this maximum point. Now, as we can see that this maximum point is a function of the terminal voltage. This is the voltage which is impressed across the solar cell or panel, and we can view it as if we are changing the load resistance which is connected across this panel. So, this is like these are these typical load lines. So, for example, if we have a partially shaded condition, then we would like to operate it at a particular voltage, let us say corresponding to this point. Now, at that voltage we would like to have the resistance which a load line which cuts this characteristic exactly at that point. Now, if we had a load, of course, a variable resistance which automatically we could keep on varying, then it would have been fine. I mean, we directly take that energy and drive that load, but then nothing else happens, rest of the world does not get that energy. So, what the obvious answer is, we have some little box, some middleman in between, which kind of modulates the value of the fixed value of load resistance and presents it to the PV cell as if there is a variation, okay, as if we are actually doing that variation. Now, this is modeled as, I mean, this is exactly where the power electronic converter comes in. This is not a real transformer, this is just a model, okay. So, and its transformation ratio is a function of what is called the duty ratio. I mean, all power electronic converters are switch mode devices. So, you have a bunch of switches and you just turn them on or off. I mean, that's and sequentially at high frequencies according to a particular algorithm. So, that algorithm is what is called the modulation strategy, and the final on off time history of that is what is called the switching function. Okay. So, now this is conceptually the crux of the whole matter. Now, this is what it that is what we really actually do. I mean, this is known as by several names. Some people call it perturb, observe. A variant of that is called incremental conductance method, and so on. I mean, this has plenty of names. Okay, but this is by far the most popular tracking method, whether it's for solar or for wind systems. This is by far the most popular method. Now, and this is pretty intuitive also. So it's like once we decide on, so we need to understand that this does not converge exponentially to the final optimal point. Okay. So it goes into a limit cycle. So within that limit cycle, it traverses, the limit cycle is centered around the maximum point. So that's exactly what it does. Now, the amplitude of that limit cycle is controlled by the choice of that perturbation. Okay. So let's those are consequences, but how does the method go? So initially, let us say we start wherever we are, let us say we have started at this point, and we just measured the terminal voltage and the output current of the PV panel or the set of panels, and calculate the power. And then what we do is, okay, fine, since we have already measured the voltage, we just give it a small little kick in a particular direction. Now, that kick is pretty important, how hard we kick it and in which direction we kick it. Okay. So, I say that initially, let us for the taking the general case, if we are starting from open circuit, that first kick has to have a negative sign, because you can't increase the voltage further. If you are starting from short circuit, obviously the first kick would be positive, because you can't reduce the voltage further. Okay. So, that decides on where is your starting point, and you could choose. So, assuming that you have chosen some magnitude, I will come to what the consequences of choosing that magnitude are. Once you have chosen a magnitude, maybe you just give it a push, and let us right now assume that I have a way to exactly control the terminal voltage of the solar panel. I have the, by some means, trust me, we do. So, supposing we do that, then we give it a perturbation, and then the terminal voltage increases to a particular value. Now, we saw in the previous curve that the power was a function of the terminal voltage. So, the power will also change. We still do not know which direction it will go, but the power will definitely change. Okay. So, we calculate the new power. Okay. And then we figure out, this is the observed step, that we figure out, okay, we had calculated power in the previous step, we have calculated power in the present step. So, which way did the power increment go? Was the increment positive or was it negative? If it is positive, then we keep on going in the same direction. If it is negative, we just reverse our direction. So, that is our final decision making step. Okay. Now, so this hill climbing method is also sometimes known as the perturb observe method. It is just the same thing. The incremental conductance, okay, you put in a few terms in the denominator, and you could convert this whole equation again to look like as if you are dealing with conductance rather than the sign of the power increment. This can be interpreted in several ways, but essentially the crux of it is just this. Okay. Now, there a few words of caution. This step is the size of this step is quite critical. If one chooses a very large step size, then one reaches very close to the optimum in a very short time. It reaches there very fast. But then once we have reached there very fast, our limit cycle amplitudes are also very large. The larger the limit cycle amplitudes, the greater is the reduction in the average energy harvested. Okay. So, if I keep so it just cuts both, you go too far in one direction, you get cut in the other. So, that means you want to get a very fast response and you keep a very large value of this perturbation step, you reach faster, of course. But once you reach there or close to the maximum point, then the whole average energy that you harvest out of it, that goes down. So, now, so there are certain annealing methods which say that, okay, fine, I start with a large value of delta Vt, and as I keep on and I detect that I am inside a limit cycle, that I can detect. I mean, if I look at my previous 2 or 3 values of V and I can predict, figure out that I am in a limit cycle, and then I start reducing the amplitude of this perturbation step. So, now coming to inverters, I mean, we all know why it's needed. So, by far most of our real workhorse appliances are based on AC. Okay. I mean, for example, a geyser or a refrigerator or a pump are all, still they are the most economical, all right. Although there are this doesn't run on, this animal doesn't run really on AC, the LED runs on DC, but then there is a converter there. Even the AC also, the air conditioner, I mean the motors, all of these run on AC. Now, there is the appliances, the kind of gadgets that life depends on, somehow tend to get run by AC. The kind of gadgets where convenience and business, I mean efficiency related gadgets or entertainment related gadgets tend to get operated by DC. For example, cell phones, computers, fax machines. So, these are efficiency improving devices. But what the direct livelihood devices like pumps, ACs, I mean we know in Kanpur, I mean if you do not have an AC, especially you must have felt yesterday, if you did not have the AC in the evening during the dinner, I mean we all felt, we all were waiting to go back into our rooms. I mean it was just that humid. So, these in all these livelihood devices they get to still they are mostly operated on AC, with AC. So, that is the motivation for taking that DC and energy in DC form coming out of the solar panels and converting it into AC. Now, there are these inverters. So, the inverter basically, it takes in DC, gives out AC, that is fine. Now, these are several, now there is a whole kind of huge rigmarole about how one structures the entire solar PV array. Okay. Now, this is what is called a central inverter. This means that you have plenty of panels which are organized in strings. Several of these strings are put in parallel and all of them come and feed the DC link of a DC port of an inverter, and it converts into a 3-phase AC. It gives it to whatever, usually to a utility grid, okay, through a high voltage step up transformer. That is pretty good, in the sense that it does, you have a single point of failure, and now that is good and bad, because if it fails, the whole thing is gone. But the fact is, to maintain it, you do not have to look for 20 different units, you just one has to look for only one unit. So, that is advantageous from that point of view. But this is quite suboptimal, in the sense that you do not, it does not ensure collection of the maximum possible amount of energy. So, the next step is the whole idea is to go as close as possible to the solar panel and maybe to the solar cell, but that has not been done as yet. So, the next step was the string inverters. So, you have a string, have an inverter, all these inverters are strung up in parallel, which are connected to the AC grid. Okay. Then you have multi strings. So, each of these strings are connected to DC-DC converters. So, they all have their internal MPPT algorithms working to extract maximum power from their respective strings, taking that energy, it into a fixed voltage DC, and which is connected to the DC port of the inverter. And there is again a single inverter. The DC to AC conversion is done in one step, but the intervening DC to DC conversions are distributed on a string. And this is the current I mean fairly recent thought that's going into that. This is the most this arrangement where you have an inverter which is directly mounted on the panel. It just looks like an extended junction box of the panel. Take the AC out, just the AC wires out. It usually works, gives single phase voltages, okay, single phase outputs. And then that's also pretty I mean that's logical, because the power output of a single panel is not that high. So, you would like to get a single phase output out of it. Now, this is the latest thought. Okay. I mean by latest I mean there have been a company that the pioneering company in this area is a company called Enphase. It's US. It's in the US, and they have shipped till now a huge about their latest estimates is that they have used more than 1 megawatt of more than megawatt of worth of microinverters. Okay. So, that is you gradually going into real life applications and practical applications. The only thing problem with microinverters is that the number of units becomes too large. I mean one has to manage a whole lot of things, single units, and the monitoring overhead is a little on the higher side as compared to the string and the central inverters. The central inverters, the monitoring overhead is actually pretty low, because there is just one unit. If it fails, you always keep track of only one guy. I mean this is like I mean one I mean one has one pet at home and one has 20 pets at home. So, that's the kind of difference, that's what it means. Okay. I mean you may have one big Labrador, or maybe, and once you have 20 small kittens, I mean you still have to take care of all of them. So, now microinverters are this is what we are the recent focus is on, the whole research focus is on. So, these are all the interesting stuff. Now, I will just quickly go through why this is these central inverters are suboptimal. Now, I'll just take any of these two strings, and let's assume that this is the first string is in what? Yeah, one of them is in bright sunshine and the other is in slightly shaded condition. I mean let us say there is a building close by whose shadow is coming directly and falling on that entire string. So, that is obviously going to generate less, because the solar intensity of sunshine is less there, and the one which is brightly lit will generate more. So, that is where we are. So, therefore, if you just recall that for the PV curves for this shaded one would look something like this, whereas the one which is brightly lit would look something like this. So, once we now the shaded now what is important to note is that if the shaded string had been brightly lit, then its VI IV characteristic would have been exactly the current IV characteristic would exactly be the blue one. So, they would have been exactly on top of each other, because they are identical. I mean, once one creates an array, all the cells are generally chosen to be, the panels are chosen to be identical. So, double of this is what, double this I2 is what the we would expect to, is the current that we would expect to see coming out of this particular pair of strings. But the moment this is shaded, there are two things which happen. One, due to shading, the maximum power point slightly shifts. It is not going to remain exactly at the same voltage as it was for a different sunshine intensity. So, now once you have split these two, and its amplitude is also obviously going to be lesser. So, once one adds these two curves, well, we would have expected, ideally the money that we have paid is for this dashed curve up there. I mean, we paid for the cells, so that is what we have invested for. But just because of this shading, the solid curve is what we actually get. Now, this so we lose this much of this. Now, this is only power. If this situation exists for a certain duration time, then you multiply it by the interval of time, and then that is the amount of energy one loses, okay, as compared to loses in the sense has to be understood in a particular way, that we have paid for it upfront. I mean, it's not like you are burning 10 tons of coal and getting some energy and you paid for it, and then you don't want that energy, you don't pay for it, so you don't get the energy. It's not that way. Here it says that, okay, fine, okay, you want energy for 25 years, fine, but pay up now. So, it's already paid up energy, energy already paid for. So, once it's already paid for, we would all obviously want to get it back as fast as we can and then be in profit, otherwise we won't be interested in it. So, any loss like that, so that in that sense it's a loss. So, any loss like that is going to obviously affect. Now, that's these are kind of, so this does not give us the maximum that we could, and this peak is, if one sees, just because these two peaks are appearing at different voltages, the height of this peak is less than the sum of these two peaks. So, even under that condition, whatever we could have got, we are still not being able to get that, just because we have I mean, strung them up in this particular configuration. This is just consequence of the topology, nothing else, the way we have connected them. Okay, fine. Now, we take the next step in. Now, earlier, of course, they were supposed to, what you could do, the constraint in this case was that both the strings have to share the same voltage. Now, the moment we go into a string inverter, the constraint becomes exactly its dual. That is, now we are not talking about two strings, because this string is completely decoupled from the next, because they have different inverters to do the energy conversion. But now the constraint comes in the form of all the panels in a string are forced to share the same current. I mean, they are connected in series, so there is no way out. Now, once that criterion is plugged in, we get curves of this type, and there is also one more important story, that these panels have what is called a bypass diode. For example, if they are connected in a string and the string current is way more than the current which is generated by that particular panel, then the rest of the string current completely bypasses that panel, and the energy, whatever little energy it could have generated, is completely foregone. So, it is kind of, you just forget about it. Now that bypass diode kind of kicks in somewhere in this region, okay, and so again you get we get this kind of a, so this is current in this axis and power on this axis. So it's just the axis have been just shifted around, rotate. It's still suboptimal, okay. So that now this obviously can be avoided if we could under any given situation just take the whatever the maximum a panel can give, we just take it. I mean make sure we get that. So these are some of the features. The estimate, this may be a little bit of a kind of an insurer's promise. I mean insurance agents talk like that. But it's still in the range of a best case situation would be about a 20% increase in the energy. But if you if one thinks about the amount of money that goes into it, a 20% improvement in the returns is something that we can't ignore. Okay. So that's why that's the chief reason why more and more people are thinking to go in that particular direction. The advantages are the cabling losses, the DC cabling losses are reduced. Now the second advantage is that the DC protection is requirements now what are kind of minimal here. The problem is once I put several panels of these panels in series, total DC voltage turns about at least about 400 to 600 volts. That's how typically these strings are operated. Now a human being, if he touches that 600 volts, any operating personnel, he is dead before he even can think of removing his hand from there. Of course, if he whether he can, that's a different thing, but he is dead. That's it. So now and the worst part of protection, I mean switch gear and protection like breakers and switches in DC is that we don't have a zero. So if there is a current arc which happens when you open a contact, it doesn't naturally die down, which in AC it does. So having a switch gear and protection in DC for DC circuits, especially when the voltage is slightly on the higher side, is always a challenge and a nightmare. Of course, there are solutions. There are DC switch gears, but on a RMS current to RMS current equivalent. Let's say you have a 100 ampere AC switch gear and a 100 ampere DC switch gear. The cost is around 4 to 8 times. I mean, the DC is obviously more expensive. So that's the kind of expense we are talking about, okay. And protection is essential, you can't really ignore it ever. So so these are the kind of advantages. There is no DC wire lying around and there is no high DC voltage anywhere if you have a micro inverter based solution. Okay. Now these are of course relevant to both micro inverters as well as string inverters. There are several of these configurations that one can do. Now the first is a direct conversion, that whatever the DC one gets directly convert it into fixed frequency fixed voltage AC. Okay, that's one option. The second option is people want to take it a little slow. So you would say okay fine, I have a variable voltage DC because I want to vary the terminal voltage of the PV in order to extract maximum power and then convert it into a fixed voltage DC. And since I have a fixed voltage DC, it is much easier for me to convert it into a fixed voltage and fixed frequency AC. So okay, so that's where the two-stage topologies come in. And some people also do a direct DC AC conversion. This is a high frequency and then a AC step down kind of a cyclo converter which directly talks to the grid wherever the AC load is. Now these are now one can also classify it under as in the category of either it's isolated or non-isolated. By isolated, what is meant is that the load circuit and the source circuit do not have any common potential between them. Okay. So, galvanically all the if you look at the load circuit or and trace every point, go to every point in that circuit, every point has a potential, right. None of those potentials have any relationship with potentials, not potential difference, but any relation with the potentials on the other side, on the source side. Now, this can be done in two ways, the isolated, there are advantages of doing that, I mean it is obvious, I mean we all know that. So, one can do it with a line frequency transformer. So, this is 50 hertz in India, or one can do it with a high frequency transformer. Typically these transformer frequencies are they operate at, let us say, starting from about 1 kilohertz, they still go up to 10, 20, even 200 kilohertz transformers are also thought of. In fact, we did one work where we had a transformer which was about 200 kilohertz. So, there was a resonant tank and all that kind of stuff. So, and of course, one has the third option, which is have no isolation at all. So, now I will just end with two of the examples that we did. So, this is for a two stage. So, we said that it could be a single stage or a two stage. In the two stage, we normally take the route that we take the variable voltage DC, convert it into a fixed voltage DC, which has of adequate magnitude such that it can be converted into line frequency AC. Now, this is what we now the requirement, one of the principal requirements of this stage is a very high voltage gain. Now, normally although we all know I mean boost converters, the name boost converters immediately comes to our mind. Oh, there is a boost converter, so why do we worry about it? We worry about it because is that unfortunately boost converters, although they say theoretically it can give you infinite voltage gain, it does not. In fact, if there are non-idealities in the whole converter circuit, the gain actually, where theoretically the operating point at which theoretically it predicts infinite gain, the real gain at that operating point is actually 0. So, it is just opposite of what it promises theoretically in that region. Okay. So, it has its upper limits of gain, and if you want to push the voltage gain in a traditional boost converter, then the efficiency becomes way poor, very poor. So, we just cannot afford that in such applications. So, this is one such, and okay, the output voltage could be controlled by the duty ratio, that is the controlled variable, and one design variable, which is the turns ratio between these two windings. Ignore this one, this was just the magnetizing inductance of that branch. I am not getting into the details of this, but one critical thing is, if you ignore this, assume that this is a short circuit and ignore this branch and this capacitor, this is exactly what is called a flyback converter. Now, once we took the flyback converter and just twisted it around a little bit, one important thing about the flyback converter is that the energy trapped in the leakage always gets lost, and in any particular pair of windings which are magnetically coupled, there is always a leakage. I mean, one cannot make any two coupled windings without any leakage. I mean, forget it, I mean it is just not possible. So, since it is not possible and they have rather unpleasant effects on the circuit, one of the unpleasant effects is when you one turns off the switch, the DI/dt will destroy the switch. Now, to prevent that, one dumps this energy into a capacitor and then burns it off in a resistor. So, what this entire circuit is, instead of burning it off, we are trapping it in that capacitor. Part of when this switch is off, part of it is pumped back into the source, and part of it is pumped back into the load. So, we are recovering the energy which is stored in the leakage inductance, and thereby we are kind of improving the efficiency. So, that is the whole trick of that work. So, this is what we had to go in for. I mean, is obviously not a linear, exactly a linear system. So, this was after the linearization, the small signal model of it, and this is what the output quantity was the output voltage VO, which we saw at the capacitor, and the input variable was the duty ratio here. I mean, we understand what duty ratio means. It's the switching function. And so, we get a pretty nasty looking transfer function, but once we plot it, this is what we see. What is important to see is that we see a resonance, not very sharp, but still one, but that brings the phase angle pretty close to 180 by the time it is over. So, we are kind of, if we want a stable closed loop, we must stay away from this region. So, that is why we went in for an integral algorithm, integral control, and that is where we got the crossover. So, we wanted a 4 milliseconds of settling time, and we got a decent amount of phase margin. So, that at least we know that we would be stable, and this is what we got. So, we designed, what we tested it under was, we gave step changes in load, up steps and down steps, and saw how the response was varying. So, these were, so during a down step we expect a little bump in the output voltage, a little drop in the output voltage when there is an up step. So, these are expected. I mean, this is a dynamic system, this will happen, but what is important is how much time it takes for the disturbance effect to go away. So, what we designed was 4 millisecond, what we got was 4.3. Okay. So, that is where we are. And if regarding the efficiency, we tested it at two different input voltages. The efficiency, yeah. So, this is something like about 96, yeah, in the range of 96% efficiency. What is important is at the part load, it is also pretty flat. So, even if the load reduces, the efficiency does not degrade. There, sorry, that is why, yeah. So, this about 96 the maximum. So, that is the euro. Euro is a weighted measure of the efficiencies, because at various different loads the efficiency does not remain the same. Okay, this is, I think we can skip that, but the repercussion of the grounding issue is that appearance of a ground current, and it has a degradation effect on the module, number one. Okay, and of course, it leads to noise pickups. It usually is a high frequency interference. So, if you have some circuits operating in the neighborhood, that is also going to get affected. So, now the present option is, okay, let us have, yeah. So, these are the effects of it. Now, if we could avoid this pulsation in the potential of any of the PV terminals with respect to the ground, then this whole business of ground current can be significantly reduced. So, the kind of strategies that presently people look at when it comes to microinverters is, whatever is the grid neutral, have the entire circuit reference to the grid neutral. So, we want to get an AC out here, yeah, whether it is a standalone load or in a grid connected operation. We always have a common potential between the load circuit and the source circuit, yeah. Now, if it is a standalone, if I earth this particular terminal, then there is the panel, the panels here obviously, it is shown as V in, but this is the panel. Okay. So, if it is earth, then this terminal is always more or less at a fixed potential with respect to the earth, and the lower potential is anyway at earth. So, there is no high frequency variation in the panel terminal voltages, and so there are no ground currents. Okay. So, this is one of the present approaches that are being taken, yeah. And this is also slightly derived circuit. I mean, this is not available straight off this very recently, just probably last week, it got we got it accepted in transactions. So that's why it's pretty hot from the oven. Okay, so and these are the nasty stuff that we need to go through. The important thing is this circuit operates in two distinct modes. In when the voltage output voltage is supposed to be positive, in the positive half, operate in what is we call it as mode 1, and when in the negative half it operates in what is called as mode 2. Now, what we do is in mode 1, this switch 2 is S2 is permanently kept on, and this switch 2 is permanently kept off, and switch 3, this is permanently kept on. Whereas in mode 2, which is the negative half cycle, switch 1 is permanently kept off, this one is permanently kept off, switch 4, which is this one, is permanently kept on. So the way we operate it is kind of, that's where the trick is, and the remaining switches are all operated in a pulse width modulated manner. What is good is, in the ideal case, the gains, the voltage gains in both the halves have the same expression. Okay. Now, as I said, I do not want to repeat the bad news so much, but designing the controllers are a little bit tricky, because this is a fourth order system. Okay. Now, that makes it a lot messier. If one opens standard textbooks or even most of the converters, the maximum people go up to is, okay, a second order converter, one inductor, one capacitor, and fine, let us finish the job, well done. But yeah, we can't help it. So, we have them and we have to make sense out of it, do business with them. So, that's what we have to grit our teeth and go through that. So, what we do is, there is a current program mode control in power electronics, and what happens is that one normally chooses a variable which is continuous in time. I mean, continuous in power electronics, we do not understand the word continuous in a slightly different way. What we mean is that we do not want to look at a variable which has extended periods of zero dwell. Okay. So, in one case we find that that variable, the choice of the variable, we actually apply certain criteria and see which is the best, and we see that I1 in mode 1 fits the bill, whereas I2 in mode 2 fits the bill. So, we have to kind of jump between reference quantities as we change modes. That is not so difficult, because the voltage generation, the reference voltage is what we generate. Okay. So, or is a reference which is coming from outside. So, that is a known variable. Okay. So, that is not such a big problem, and these are the, of course, the current program modes. So, we try to control the variables that we want, and that variable in turn governs the output quantity, which is V2, the output voltage in each of these cases. So, the form takes there is a slight difference between these two forms. So, depending on whichever mode we are operating in, we need to stick to that. So, these are the performance results. So, and this is the standalone, there is just a voltage reference, this is not the grid sinusoidal voltage. That is the exact output voltage waveform V2, and that is for a resistive load. So, you see that the voltage and current are exactly in phase, and there is an RL load. Okay. So, even for reactive loads it can do, the voltage waveform is pretty good. I will just come back to that a little later. And this is the worst of all, and this is when you have one has put a diode rectifier onto it, and the current is practically rectangular, but then there is not much of deterioration in the shape of the output voltage. These are all, the first three are all standalone applications. So, you do not have a voltage source which is defining the shape at all. So, that is just like completely in open domain, and whereas the voltage THDs in the first case is 2.7, 3.6 in the second case, and 4.1 in the third case. the limit is 8% as per the IEEE standard. So, that is well within the limits that could have. And okay, and this is for the grid connected operation. By the way, this was the grid voltage. So, you might appreciate that the grid was a little more nasty than the quality of the output voltage that we produced in standalone operation. So, but even then we could manage to control the current with a THD less around 4.3%. Again, the limits are, I think, about pretty close to 8, it is about 7 or 8, I mean I just exactly forget the number. So, we are again well within this THD numbers. Okay. So, thank you, and thanks for the attention. Any questions I would like to take it.